All right, guys. Hello and welcome to the last. It's also going to be sort of our farewell session, but not really because we would still have our P5s which are still left. So, all right. So today, what we are going to do is that we are going to have a look at all of the syllabus at a glance. And while doing that, we will be talking about some mistakes to avoid, so some general tips and tricks, good questions regarding each of these chapters, and also a sort of paper prediction that we are going to discuss in our session today. All right, so let's start. So I've split this up into some different sort of chunks on the topics that I've sort of grouped together. I've tried to group together related topics, but then just to make the chunk, basically to make a proper chunk, I've also grouped together an unrelated topic. So the first one we're talking about is circular motion, and circular motion and gravitation, you guys know, are very closely linked. And alongside that, we also have oscillations in this first chunk of our syllabus. So regarding circular motion, you must be able to define certain things like the radian measure. How do you define this? So this sort of stuff you must be able to define. Next, with circular motion, you must be able to talk about these problems where you are asked whether contact will remain there or whether it will be lost. It's something which is discussed in some of the videos on the platform, which are those 2021 videos, and how centripetal force varies. There was this one question, I think it was March 23, where also something really similar to this was asked. Yes, the angle produced at the center of a circle given arc length and radius are the same. Yes. We don't say suspended, we say subtended. Let me write it like this. It's subtended. Or if you guys don't like this, you can also just say produced. It's just a fancy word. You can choose not to say it. So yeah, so that's what this is. Then when we go on to gravitation, the chapter of gravitation, there are a lot of derivations and definitions in this chapter. So for example, with definitions, you might be asked the definition of gravitational field strength, gravitational potential, Newton's law of gravitation. Derivations include Kepler's third law, how you get the relationship for the gravitational field strength from Newton's law of gravitation. Also in the past, you have been asked how you get the potential energy equals mgh relationship from some of these. So that's also asked. Something else which is really, really important, especially in the more recent examinations, is the idea of geostationary orbits. Do we say the velocity increasing type of thing? I'll show you a question, Rania. Just wait a sec. For variations, I will show you a question where the centripetal force is supposed to change. But yeah, that's what we're talking about. So for example, imagine that if a car is going around on a track, if it's looping a loop, so weight will always be there, but the centripetal force changes because of the reaction force changing, right? So that sort of thing. So that's what we are going to talk about. So that's what I mean by variation. Kepler's third law, is that directly tested? Yes. You can be asked to derive this. You can be asked to use this in a calculation. You can be given a graph and you could be asked to work with it. So something which is very, very important is geostationary orbits. Whenever in your question, whenever you're reading something and you see this word orbit, you should be thinking of this idea that the centripetal force for orbit is provided by the gravitational force. This is what you must think of right at the moment you see this word orbit. And this then obviously leads to Kepler's third law, and that may be used in different ways. But a geostationary orbit is a very special type of an orbit. Whenever the examiner wants to tell you that this is a geostationary orbit, they will use some wording similar to this. There would be, for example, a satellite or something which appears or is, so appears or is at a fixed position above the planet's surface. Right? This is the word that would be used. And this is to tell you that this is a geostationary orbit. Because with geostationary orbits, the idea is that whatever is this thing which is in orbit, it always remains at the same position relative to a viewer from the planet. Right? So it appears or it's always at a fixed position from a planet's surface. And there are these three conditions which are required for a geostationary orbit, which is that it must, actually let's write like this. So it must have the same time period. So same time period, same direction of rotation as whatever planet we're talking about. And it must be in an equatorial orbit, or it must be in an orbit in the equatorial plane. Right? So this is the idea here. Where does the time period of 24 hours come from for Earth? If that thing has to appear at the same point, always above the Earth, so it must have the same time period of rotation as well. And it must also be obviously moving in the same direction, right? So that's the idea about geostationary orbits. We'll also be looking at a question from very recent papers here. Then you obviously have a lot of graphs in the chapter of gravitation. You have the graphs for gravitational field strength and the graphs of gravitational potential. And then you also have graphs for uh, how the gravitational field strength or how the potential is between two masses. That's really important. There's also this concept, which I think is on a video on the platform, in which we have to find the minimum speed, and that I have handpicked today for us to work on. The satellite has the same angular frequency as the planet, so yeah, that's fine. That would basically, you can write this in place of number one, right? So same time period would mean the same angular frequency as well. Yes. So yeah, we'll be looking at this question in a while as well, because again, the thing with A2 is that I can't really talk about a lot of the stuff without having a question in front of me, because it would just appear so vague. Energy of orbits is something which has been started to be asked a lot recently again. It was also asked in the March 24 paper. I'm pretty sure I have it open here on the side. If I don't, let's pull this up. Then I'll be referring to this periodically. So energy of orbits, escape velocity. So what velocity do you need to completely escape the gravitational field of the Earth? This is also a derivation. It's also a concept in and of itself. Then for SHM, you have defining equation. So A equals negative omega square X. And you must be able to use this in the context of graphs, or if something else is given to you, and how do you show that something is in fact obeying simple harmonic motion. So that's something which is obviously very important. And then also the sine and cos shapes for all of these simple harmonic motion questions. I feel like that sine and cos shape is something which can turn up in your paper, because that has not been asked for quite some time now, but it is explicitly part of the syllabus. So I just feel like students have been slacking off on those, expecting it to not come in your paper, but I feel like it is going to come in your paper tomorrow, right? So the idea is that, for example, if you study math, then it's very easy that you can take derivatives of the displacement that gives you velocity. Displacement of velocity gives you acceleration. But if you're not a math student, so you can always use this idea that if my displacement is a sine function, and why do we use a sine function as compared to something being a cos function, is that if something starts out from the equilibrium position in its oscillation, so the idea is that the velocity would be a cos function and acceleration would be a sine function back again. But whenever you have a cos coming in, the sign is going to change, right? Similarly, if you have displacement as a cost function, so this means that it's already at some amplitude, and that's when it begins to oscillate. Then V is sine and A is cos back again. But after a cos, again, we have a negative sign, right? So each time you have a cos, after that, the sign changes. So cos, then sine changes, cos, sine changes. So that's how you use the different equations. Yes, that's exactly what I'm talking about. X equals x naught sine omega t. I've just not written it out entirely. But this is exactly what I'm talking about. All right. And from this, you must know that max velocity is omega x naught. Max acceleration is omega x naught squared. So that sort of thing, right? You must know that. All right. So it alternates between sine and cos. And after a cos, we have a sine. That's how this goes. Then energy of oscillations is also something which is now asked more and also in a slightly different way, as we'll see in those example questions. So again, pretty much as with the videos that you guys must have watched from YouTube, which was the March 24 solution and the March 24 P5 solution as well. So I'm not doing this entirely. I'll just be talking about some of these nuances of how do you solve these parts. So define gravitational potential at a point. So work done per unit mass and bringing it from infinity. Again, another related question to this is why is gravitational potential always negative? And that is also something that we've talked about in the March 24 paper. I want to talk about the later parts of these. Unit positive mass is incorrect because mass is always positive, right? It's not really wrong. It's just not required. So Artemis is a spherical planet that may be assumed to be isolated in space. Variation with distance x from the center of the Artemis of the gravitational potential is shown. So this is the phi versus x graph. Always look at the multiples of 10. So this is x, which is also in 10 to the 7, phi, which is also in 10 to the 7. Radius of Artemis is given, determine the value of phi on the surface. This question, I think, is also on the platform, this entire paper. So the idea is that if this is your surface value, so you just use phi equals negative gm over r. The mass was given above. The mass is not given. All right. Yeah, so 4,800 kilometers. This 4,800 kilometers is basically this 0.48 into 10 to the 7, whatever this last value is. So we just needed to read off this value to this point, which is what the potential would be, right? So that's the answer to this one. Once you find phi, then you can use phi equals gm over r here and find out the mass. And then finding gravitational field strength is also not very difficult. It's capital Gm over r square. Now that you know m and that you also know the radius, finding this is very straightforward. This part 4 is something that I do want to talk about. A satellite is in an orbit at a fixed position above a point on the surface of Artemis. So just an orbit tells me that this is Fc equals Fg. But this orbit being such that it's always at a fixed position above the surface of Artemis means that this satellite is in a geostationary orbit because it always appears at the same position. And now if it's in a geostationary orbit at a height of this much, wherever the gravitational potential is this much, so I know whatever the time period of rotation of that satellite would also be the time period of rotation of Artemis. That's the logic at play here. So with this phi, I can find out the r value for it from the graph, right? Whatever this height is. So once I have that radius, then I can use Kepler's third law to find out the time period of rotation. Just this one time, I'm going to do Kepler's third law derivation, Kepler's first law derivation here, which is that gravitational force equals Fg If I write this as mr omega square or as mv square over r, you know this makes no difference. And by Newton's law of gravitation, gmm over r square, m's cancel out. Omega I can write as 2 pi over t. So this becomes r, and omega is basically 4 pi square over t square. If I also cross multiply by this r square here, this becomes r cube equals gm. Here, because I need t, let's make t the subject. So t square would be 4 pi square r cube over gm. Right? So then I just plug in the values, 4 pi square. R is what I would get from the graph corresponding to this value of the potential. G, I know it's a constant. M, I found above. And then I just plug all of this in here and find out the answer for the time period. Right, so this, in my opinion, was one of a slightly tricky question, especially for people who did not pick up on what this first line means. Right? So that's the idea here. Now, this question related to gravitational potential is what I want to talk about. This is that minimum speed question, which is really tricky. So in this question is a time period initially in seconds. I mean, yeah, so exactly. So what this time period will turn out to be will be in seconds, right? So to convert this to hours, you would then have to divide by 3600, right? So thank you for the catch. Yes, that's what you have to do in this one. So two stars A and B have the surfaces separated by a distance of this much, illustrated in 1.1. Point P lies on the line joining the centers of the stars. Distance x of point P from the surface of A may be varied. Variation with distance x of the GP at point P is shown. So you see you have a graph of 5, which is in 10 to the 8 versus this, which is in 10 to the 12, right? Now, whenever you do have a graph, it's also useful if you start thinking about this stuff beforehand. For example, you know that the gravitational field strength is the negative potential gradient, right? This is stuff you know. So if you see here, you can see that there is a point where the gravitational field strength is like this, then it's like this, and then at some point it also becomes 0. If I look here, this is the point where it becomes 0 approximately. So I know this must be the null point where the gravitational field strengths cancel out. Hence, the gradient of this graph is 0 here. And then it starts to bend in the other direction. So here the gradient was upward sloping, here the gradient is downward sloping, which just goes on to show that previously if the gravitational field was having this mass moving in some way, after we pass this null point, it's now moving in another way, right? That's how gravitational fields work. When at a middle, when they are both equal, they totally cancel out. If it moves slightly to one part, so it would be attracted to that mass. If it moves slightly to another part, it would then be attracted to that mass. So that is what we do for ourselves, even before reading the questions the examiner has laid out for us. So now we look at the question. A rock of mass 180 kg moves along the line joining the centers of the stars from star A towards star B. Use data from 1.2 to calculate the change in kinetic energy of the rock when it moves from 0.1 into 10 to the 12 to 1.2 into 10 to the 12. So 0.1 is right here and 1.2 is right here, right? So again, this is not really very difficult. We need to find the change in kinetic energy. So the change in kinetic energy would numerically be equal to the change in the gravitational potential energy, which we can find as m delta phi, right? So phi here is minus 10, and this is minus 14. So if I look at this as a change, so this is 4 into 10 to the 8. This is delta phi, and m, the mass of the rock, is 180. So I just multiply them together and I get the gravitational potential energy change or change in the kinetic energy. Now, if I look here, it also asks me state whether this change is an increase or a decrease, right? So now this is what we must think about really calmly before going on to make a decision. So our gravitational potential has become more negative, right? It went from -10 to -14. All right. So the gravitational potential became more negative. Now, what does being more negative mean? If I actually do this delta phi, so phi final minus phi initial, so this is -14 minus minus 10. This became -14 plus 10, which is -4. Right? This is what I used, but I just wanted you guys to see the algebra behind it. So the gravitational potential has decreased, right? If the gravitational potential has decreased, this means the gravitational potential energy has also decreased. So this means that this change in kinetic energy would be an increase. That's the idea at play here. No, you don't assume anything for null points. It's just how it is. For null points, for this to be a null point, this means resultant gravitational field strength is zero, right? So the gravitational fields of both the bodies must cancel out. So that's what was the idea here. So here, because the gravitational potential gets more negative, this means the gravitational potential is decreasing. So this means that the kinetic energy must increase. The next part is what I do want to talk about. So at point X, where X is 0.1 into 10 to the 12th meter, the minimum speed of the rock is V. Determine the minimum speed V so that the rock reaches the point where X equals 1.2 into 10 to the 12th. I hope you guys looked at this reference because this is such a good question that it deserves to be done separately. In a time where we do have a lot of more recent questions as well. This is 2016, right? So I think about the time maybe when I was giving my A levels. So the idea here is this, that if we are talking about the minimum speed, what does this really mean, the minimum speed? The idea is that if my object is here, so visually this means that if my object is here, if I wanted to go all the way till here, one way to do this is to push it all the way. Push it all the way from one end to another end until it actually hits the surface of star B. But is that really necessary? And the answer to that question is no. It's not really necessary. And hence the word minimum speed. You only need to push it to a certain distance where the gravitational field strength is zero. Because if it does reach this point, it will automatically start to be attracted by the other star B, and it would be pulling that rock towards itself on its own. We don't need to push it all the way. We just need to push it to that point so that pull, this pull that this experiences, so that this ends, and now this one can start its job, right? So this was the idea of minimum speed here. So if you look at this gravitational potential value, this is -4.2 into 10 to the 8. So in this case, I don't need to go all the way from -10 to here. I just need to go to here. So -10 to -4.2. So 10 minus 4.2 is what? 5.8. Right, so 5.8 is my delta phi here. So 5.8 into, what was it? 10 to the 8 joules per kg. And now here the calculation will also start to make sense, and you can also double check the answer to that previous part. Here the idea is this. Yes, the mic. Hello. 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 All right. Yes. So the idea is this, that here the gravitational potential was increasing. Do you guys see this? The gravitational potential increased here. And it makes sense that because the gravitational potential is increasing, the potential energy is also increasing. And hence the kinetic energy would decrease. This is why we're talking about the minimum speed. What's just the speed with which we must throw it out so that it just comes to rest here, and then the second one starts pulling it, right? So the gravitational potential energy is increasing, and here, in going from here to here, the kinetic energy would be decreasing. So then we have this delta phi, we again use m delta phi, and we set that equal to half m v squared, right? And that's how we would do this. Again, you don't even really need m here. You can just break with this to find the minimum speed v. Don't two positives repel? This is not charge, this is mass, right? So both of these would be attracting that point mass. Masses always attract. So that was the idea which was at play here. This is another recent paper, Summer 22, paper 42, question number 4. Part A state what is meant by resonance. So this is also pretty easy, honestly, which is that the external frequency provided equals the natural frequency causing a large increase in amplitude of oscillation. Right, so this is stuff that we already know. Yeah. So part B, 4.1 shows a heavy pendulum and a light pendulum, both suspended from the same piece of string. The string is secured at each end to fixed points. Both pendulums have the same natural frequency. The heavy pendulum is set oscillating perpendicular to the plane of the diagram. As it oscillates, it causes the light pendulum to oscillate. 4.2 shows the variation with time of the displacements of the two pendulums for 3 oscillations, right? So these are how they are oscillating, with the heavy pendulum oscillating with the dotted line and this one being the lighter one. Variation with time of the displacement of the light pendulum is given. This is now a expression for the displacement, and you need to extract from this the time period. So the idea is that this is x naught sine 2 pi ft. So this 5 pi is really 2 pi f. So 2 pi equals 2 pi f equals 5 pi. So pi's cancel out. And you can also write this as 2 over t equals 5. So t equals 2 over 5, which is 0.4 seconds. On 4.2, label both of the axes with the correct scales. Use the space below for any additional braking that you need. All right, so what do we need to do? We need to label what? Oh, so we need the correct scales. All right. So this is for the lighter pendulum, right? This is 0.25, and this must also be in centimeters then. So what is 0.25? If this is 0.25, so this must be negative 0.25, and this would be negative 0.5, negative 0.75, and similarly 0.5 and 0.75, right? So next we also have to label the x-axis. So time period of oscillations of the light pendulum is 0.4 seconds. So this is 0.4, this would be 0.2, this would be 0.6, 0.8, 1.0, 1.2. So that's the complete labeling of these scales. I hope this is not a problem. This is really easy. Determine the magnitude of the phase difference phi between the oscillations of the light and heavy pendulums. Give a unit with your answer. Again, not really difficult. It's more like this stuff that we have in AS. So if you look here, you can see basically that one is a sine, the other one is a cos. Right? This one starts from the top like this, and this is how it goes. You can also relate it to this idea that the peaks, if you look at just the peaks, and let's say if you don't know the math behind this, you don't know sine and cos. If you look at the math behind this, these are a quarter of a time period apart. Because with the peak here, this is the period here. And both of these have the same time period, 0.4 seconds. So 0.4 and 0.4. So these are a quarter of a time period apart. So 1/4 of either you can say 360 degrees or you can say 2 pi. This turns out to be 90 and the unit is degrees. Or you could write pi by 2 and the unit would be radians. So I'm just trying to give you a flavor of the different questions. These are like slightly out of the ordinary sort of questions. All right, next we go on to ideas of temperature, ideal gases, and thermodynamics. So with temperature, you guys must be aware of the idea of the Kelvin scale and how it does not depend on any property, any physical property. You should also be aware of how you basically select a thermometric property. How do you actually measure temperature? There's also another paper, I don't remember which one it exactly was, which does discuss this idea. So regarding temperature, with ideal gases, I guess it's a pretty much the same thing that we have each and every time. That you have your equations of state PV equals nRT. Then you also have this examiner favorite equation, PV equals 1/3 nmc square. How you reach this? So the entire derivation has never been asked ever since this came in the syllabus. But you must know how the derivation goes about. Why do you have this 1/3? Why do you have a c square? What's the arrows represent? This sort of stuff. Internal energy of ideal gases. This is also stuff that has been it's been asked like almost regularly. It's not something special for this year. So for ideal gases, we know potential energy is zero. The only energy is kinetic energy, which is then equal to the internal energy. Thermodynamics and everything, again, it's also pretty much the same ideas. So the first law, I have those questions compiled, so we'll be talking with the reference of that. What I honestly feel like students do mess up more with is the idea of thermal properties here, which is the specific latent heats of fusion, vaporization, and that stuff, specific heat capacity. Questions related to those are difficult. As compared to the other ones, ideal gases and thermodynamics are honestly easier than that. So yeah, let's just go on to the questions and see what we have in store. So part A state what is meant by an ideal gas. We've done this a lot of times. PV over T is a constant. And then you just need to talk about what each of PV and T represent. Do make sure that for T, you don't just write temperature, you write down thermodynamic temperature. So the first part in here is not really difficult. No thermal energy enters or leaves the helium gas. I guess we've also done this in one of our more recent live sessions, but I still put it in here because the later parts are good. So show that this is an ideal gas. So you just show that PV over T is constant for both of these stages. When doing the calculations, do make sure that your temperature is converted to Kelvin. Right now, this is degrees Celsius, right? First law of thermodynamics may be expressed as this. Use the first law of thermodynamics to explain why the temperature of the helium gas increases. Right? So here helium was behaving as an ideal gas, and we want to talk about why the temperature increases. So if temperature is increasing, this means obviously internal energy is going up. And if we look at the work done here, so the volume is decreasing, right? If volume is decreasing, so this means that work is being done on the gas. Somebody is pushing down on the plunger. So since you have work done on the gas. This means your W is positive. And there is no mention of Q, so this means that delta U is positive. So U goes up, and hence temperature also goes up. Average translational kinetic energy of a molecule is given by this. Calculate the change in the total kinetic energy of the molecules of the helium gas. Again, I also recall doing this very distinctly. So if you're talking about the change, that's only because of the change in temperature. Here, do take care of this idea that you don't really need to convert the temperatures here to Kelvin, because if you have a temperature in degrees Celsius or in Kelvin, the temperature difference is going to be the same anyway. So if you just do 742 minus 27, that's here going to be your change in temperature. But this is just for one molecule. For all the molecules, you would multiply by the number of molecules that you have, which you would get by the usage of this equation. All right. So that's what you would get. Mass of nitrogen gas in another container is 24 grams at a temperature of 27 degrees Celsius. Gas is cooled to its boiling point. Assume all the gas changes to a liquid. For this change, the specific latent heat of nitrogen gas is this much. Specific latent heat of vaporization is given. Find the thermal energy removed from the nitrogen gas. So it's really two energies. One energy is basically because of its loss of temperature from 27 to negative 196 degrees Celsius. And then the other energy which is lost is because of it condensing. Right? So these are the two energies. So first one, I just use MC delta T. MC delta T. And for the other one, I just use ML. Right? So mass is 24 grams, but this is in kg. So I need to convert one of these to kg. 24 over 1000. C is 1.04. And keep in mind, this is kj, but it's fine because this is also kj. And the change in temperature, so the difference between 196 and 24 is 220. And then ml, so again, this is in per kg. So 24 over 1000 times 199, and whatever this turns out to be is the answer here. Rania, did you get the question? Did you get the answer to your question? Okay. What is meant by ideal gas? Calculate the amount N of gas. So this is easy because we have N, which is obviously in moles. Just need to use this equation. Again, we just need to convert this to Kelvin. Right? Part B is what I would like to talk about a bit more. The gas undergoes 3 successive changes as shown. So it starts out at A, it's then cooled at constant pressure to point B. By removal of 48 kilojoules of thermal energy, the gas is then heated at a constant volume to C, and then it expands at constant temperature back to its original pressure and volume at A. In doing so, it does 31.6 kilojoules of work. Show that the magnitude of work done is this much during the change AB. Again, I'm also pretty sure this is what I did. Even this is what I did last year. It's definitely on the platform. So work done is just going to be P delta V. So pressure is this value, which is 1.2, and you take the change in volume, which is 0.024 and 0.08. The difference is 0.16 and 1.2. This is 10 to the 5. So 1.2 to the 5. This should give you this value right here. This one also we've done. If not exactly this one, then we've done a lot of these ones similar to this question right here. So it's remove, so if we talk about A to B, right, we just found out the work done. But again, now according to the first law of thermodynamics, we need to think whether this is going to be a positive term or a negative term. Because volume here has decreased, this again means somebody pushed down on the plunger. So this is positive. So this is positive 19 point, right? Then you get this value. BC, so this is constant volume, so nothing happens here. And are we told about something to C? So we don't know about this. And then it expands at constant temperature back to its original pressure and volume at point A. During the expansion, the gas does 31.6 kilojoules of work, right? So the gas does this work. So this time it's going to be negative, exactly. And what else do we know? Yeah. So if we look at this then, so lastly, the gas expands at constant temperature, right? So if there's no change in temperature, so this thing is zero. And then I also know that because this is a cycle, this entire thing would also be zero. All of the changes in internal energy because it has no overall change in temperature. So negative 28.8. This must be positive 28.8 so that this total is zero. And then if I look here, so this must be 28.8. And then if this is negative 31.6, this must be positive 31.6 so that this plus this equals zero. All right, so that's the answer to this one. This is what I do want to talk to you about because a lot of students have been asking me that questions like these, which are not really numerical, are what trouble them more with trying to explain these in terms of, what do you call it? So trying to explain these in terms of internal energy and the first law of thermodynamics and whatnot. So this is what we are going to talk about right now. So, all right. So state an expression in terms of work done in heating that is used to calculate the increase in internal energy. So you just need to write this out in words that the increase in internal energy equals the thermal energy supplied to a system plus the work done on the gas, right? You just need to choose your words carefully. Part B and part B1 and B3, B2, this is what we want to talk about. State and explain in terms of your expression in A, the change in, if any, in the internal energy of the ice cube, of the water in an ice cube, when the ice melts at atmospheric pressure to form a liquid without any change of temperature, right? So this is melting at atmospheric pressure, right? So this is basically a solid turning into a liquid. So how do you explain this in terms of the first law of thermodynamics? Right now, this is the question that we must answer here. All right. So internal energy, let's think about this in terms of all of these things involved. So first off, I know that if this melts, if this is going to form a liquid now, there's going to be an increase. Just a sec. Yeah. So basically the volume, here is decreasing. So you can say work is done on the system. Right? So if the volume decreases, so this is work done on the system. Then if we think about Q and W, so you know that for delta U, You also know that for melting, you need to supply thermal energy to overcome the intermolecular forces. So thermal energy is supplied to overcome intermolecular forces. All right, in reality, the idea is that the volume does decrease here. The idea is related to the answer to the question is related to what you have studied in chemistry about hydrogen bonding, right? In AS chemistry. So the idea here is this, that the volume decreases. The volume does decrease because the liquid is more dense, liquid water is more dense than solid ice. Yes, the volume has decreased, right? So that would have done. The volume decreases because of this. But here, because this is such a case of an anomalous liquid, so even if you do not, if you say that there is maybe no change to the volume, so you can also ignore this idea. The examiner is also willing to accept that. So if somebody says that volume does not change by all that much, so W is 0, that's also acceptable, right? But there is, you guys know this, the thermal energy needs to be supplied from melting, right? So the idea is that because of this, internal energy increases as the thermal energy supplied is greater than the work done on. No, just a second. Yeah, so because as a sum of both of these, the thermal energy does increase. Right? Even if you do not write about the volume part, if you say that the change in volume is negligible, which it is honestly. So yes, again, you do get the same idea. So then we need to talk about the internal energy of a gas in a tire when the tire bursts, so that the gas suddenly increases in volume, right? So the gas increases in volume here. I know what you're thinking about, Fardeen, but we can't. Because you have to use, I know it's much easier with kinetic and potential energies, right? But you are asked to explain this explicitly in terms of the first law of thermodynamics. What you could do is you could write down this explanation and use the kinetic and potential energies to double check your answer, right? Because you know that kinetic energy is going to be the same if temperature is the same, and potential energy is going to increase as spacing increases. So internal energy is supposed to increase by that reason and also by this. So you can double check, but no, you can't write your answer in terms of that. So first off is that if this suddenly increases, by the way, the sudden thing is supposed to give you this hint that pressure is constant. So the idea is that work is done by the gas. So W is negative, basically. And assume that the gas is ideal, right? So again, if this is instantaneous, so there is no time for the thermal energy to enter or leave the gas. So no time for thermal energy exchange. So internal energy decreases. Right, I remember, but I just couldn't seem to find it when I was basically selecting these questions. Is I remember that in recent years I did a question, and I'm pretty sure I did it with you guys, where we were talking about how the internal energy of a puddle of water evaporating changes, but for the life of me, I couldn't find it at all. Question number 7, electric fields, capacitance, and just to again complete the chunk, I have astronomy and cosmology here. So electric fields, the idea of electric fields, again, it's a very, very vast topic. There's the uniform electric field, there's the non-uniform electric field, there's the idea of the point charges, Coulomb's law, all of that stuff. There's the graphs. In a way, there are more graphs here than with gravitation, because gravitation, you can only have two types of masses. You can only have one type of mass, so it can only attract. But with electric fields, the charges can repel as well, right? So with electric fields, you can have a lot of type of questions. We'll be looking at some of these. Capacitance, again, is, I guess, not really difficult, but the graphs in recent times have been quite tricky in terms of the ln and the capacitor discharge. You should also understand its applications in smoothing circuits. And then you have astronomy and cosmology. Again, something which you guys would normally treat as an easy topic, but in the questions which have come in the recent papers, the astronomy and cosmology chapters have also really stepped up in difficulty. It's definitely more theoretical, it's more technical now than what it was in the first few years. So I've handpicked some questions, and then I didn't have time to do more, so I'll be doing those on the go as we move ahead. So first one, define electric potential at a point. We know how to do this. It's really similar to gravitational potential. You just swap out unit mass for unit charge. Part B is what I want to talk about. Two isolated charged metal spheres are situated near to each other in a vacuum with their centers a distance of 24 meters apart. P is a variable distance x from the center of sphere x on the line joining the centers of the two spheres. 5.1 shows the variation with x of the electric potential V due to the spheres at point P, right? Now here a diagram is not given, but I will still make one small one just to show you guys some important ideas here. This is my sphere X, this is my sphere Y. And the idea is that the distances, as is also indicated in the question, are measured from the center of X. So this is my point B, right? This is that small distance X. State 3 conclusions that can be drawn about the spheres from 5.1. Conclusions may be qualitative or quantitative. Now, electric potential graphs, first off, I can definitely see the radius. So I can see that the radius of this sphere is this much, the radius of this sphere is this value. How do I know this? I know this because inside a conducting sphere, the electric potential is going to be constant. So because this was measured with respect to x, I'll say that the radius of x is 2 meters and the radius of y is 2 meters. So that's the first thing I see. Then I can also see this as a Vx graph. So I know that taking the gradient, I can basically get the electric field strength, right? So I know E is negative delta V over delta R. So if I think about the tangent here is much steeper as compared to the tangent here, right? So I will say this, that the electric field strength at X is much stronger than the electric field strength at Y. So electric field strength at X is much stronger than the electric field strength at Y. Y is what negative? E equals delta negative V over E equals negative delta V over delta R. That's just how the formula is, right? It's the negative potential gradient. There is a pretty good reason for this, but I just don't want to give it right now because it will just confuse you. But if you really want to get an answer to this, this is on the whole platform. Why they have negative signs in the video, which is titled Negative Potential Gradient. The other thing I can see is that all throughout this place, the gradients are always in the same direction, right? The gradients never change signs. So this means that this charge is always basically acted on by a force in the same direction. This could only be possible if one is a unlike charge, if both of these are unlike charges, right? So that the electric field strengths are always in one direction throughout. And I can also look at the formula for the uh, electric potential to figure out what is negative, what is positive. Again, this has no negative sign, it's just kq over r. So the charge of the sphere decides the charge of the potential. If here v is negative, this means that q is also negative. So I'll say x is negative and hence y is positive. Next one, a positively charged particle is placed at point P in V such that x equals 12 meters. The particle is released. Describe and explain the subsequent motion. So it's released from this point, right? So as you can see from here, the tangents just keep on getting steeper. So as you can see, this here was a what? A positively charged particle, right? So if a positively charged particle is placed, what is going to happen to it? First off, if it is placed at 12 meters, it's going to be attracted towards X and repelled by Y. This is the first thing, which is very obvious to say, right? So it is going to be repelled by Y, attracted by X. Then to explain the motion, so repelled by Y, attracted by X. How did you conclude the steepness? Just by drawing tangents, right? That's how you find gradients to a curve. And the gradient here is the electric field strength. So it's repelled by Y, attracted by X. And to talk about the motion here, the idea is that how it moves when it's going to move towards X, this is getting progressively steeper, right? This is how it moves, right? So the electric field strength is increasing. Now let's write this down here in symbols. So electric field strength is increasing, which also means that the force would be increasing, which also means that the acceleration would be increasing. So I would say that this moves with increasing acceleration. How do I get this relationship between E to F is basically because E equals F over Q. How do I get this relationship between F and A is because F equals ma. So the positively charged particle moves with increasing acceleration. This is another good question regarding capacitances. So this is actually a unique question because this is of a capacitor charging another capacitor. This is also, by the way, on the platform. This is also on the platform. So first it says that the capacitors are connected as shown. Capacitor has capacitance C, capacitor B has capacitance 3C. EMF of the cell is V. The two-way switch is initially at X and V is initially uncharged. State in terms of V and C expressions for the initial charge QA on the plates. So if voltage V of this source appears here, so it's going to be CV8, CV, right? And initial energy would correspondingly be half CV squared. The two-way switch has now moved to position Y. State and explain what happens to the charge that was initially on the plates of capacitor A. So when this is where the switch is now, so you know that this capacitor will start discharging across this capacitor. So this capacitor would keep losing charge, this would keep gaining charge, but it's not going to be an indefinite process. It only goes on until both of these have equal potential differences. So what I'll say here is this, that some charge of A is deposited across B until the potentials till the potential differences across both are equal. Because you know that what dictates current flow or similarly flow of charge is a potential difference. If there is no potential difference, there would be no flow of charge either. So there would be no current. Show that the final difference potential, show that the final potential difference VB across the capacitor B is given by this equation. So the idea is this, that when all of this process does end, so there would be some potential VA here, there would be some potential difference VB here, and both of these would be equal, right? So I know VA and VB at the end would be equal. And additionally, what I also know is that the charges on both of these would not be equal, but the charges, the sum of these charges would equal the initial charge. This is just conservation of charge. Charge is not going anywhere else. The charge that this loses is basically deposited onto B. So I'm going to say that QA and QB, the sum of these would be equal to CB. I'm talking about the new charges, right? So QA, how can we write this in terms of capacitance? Well, it's very easy. Now that we do know the voltages as well. So I know that A has a capacitance C. So this is CVA. And B has a capacitance 3C. So it's 3C VA or VB. If I write it, it doesn't make a difference because of this idea. But because let's say the examiner wants me to write this in terms of VB, let's use VB equals CV. Again, you see all of these C's cancel out. So this is really 4VB equals V. So VB is just V by 4. All right. Determine an expression in terms of V and C for the decrease in the total energy that is stored in the capacitors as a result of the change of the position of the switch. This was the initial energy. Now let's find the new energy. So new energy is half CV square again, half, and across A, capacitance is C, and the voltage is V by 4, and this is squared. And for the other one, it's half, capacitance is 3C, and the voltage across that is V by 4 as well. So if I just want to do this, so 16 and 2, so this would be CV square over 32 plus 3 again 16, so 3 CV square 32, right? So this becomes 4 CV square over 32. This is the new energy. The initial energy was half CV square. So I really have half CV square minus 4 CV square over 32. Don't freak yourself out over this. Just write CV square here and then just do half minus 4 over 32. So half minus 4 over 32 is 3 over 8 CV square, right? So that's the answer to this one. So now I want to also show you guys some questions on astronomy and cosmology. I'm going to refer to the March 24 paper, which has already been uploaded on YouTube. Why both have the same voltage? The idea is this, that if they do not have the same voltage, when will they stop? That's the proof by contradiction. The other proof is this, that as this loses charge, this one is going to gain charge, right? So the voltage across this keeps dropping, the voltage across this keeps building up. And when there is no more potential difference between the two, when current flow stops. All right, that's the answer to your question. Does this make sense? Because if you think about a capacitor, how a capacitor and how a capacitance is defined is basically because of the charge. That charge on the plates leads to that voltage across it. Right now, I would like to show you that astronomy and cosmology question. All right, let's start with the first few parts. So surface temperature is given, luminosity is given, you are asked for the radius. Yes, we will. Rania, why will we not discuss it? We will obviously discuss it. So radius, you are given luminosity, you are given temperature. So to find the radius, you just use the Stefan Boltzmann law, right? You just make R the subject. This is also relatively straightforward. Second part, to find the radiant flux intensity given the luminosity and the distance. This is also easy. The next part was slightly more technical. The variation with wavelength of the intensity of radiation emitted from the sun is shown in 10.1. So there's the intensity wavelength diagram, which is not really part of our syllabus. But if you remember the videos that we made, I did use this. I did use this graph to teach you guys Wien's law. Another star has the same radius as the sun, but a lower surface temperature. Sketch a line to show the variation with lambda of the radiation emitted for the star. So you know that what this one is what we call lambda max and the Stefan Boltzmann in the Wien's law, right? So if temperature goes down, obviously the peak luminosity would also go down, right? So the luminosity also goes down. So the intensity also goes down. But also because here the temperature goes down by that inverse proportionality between the max intensity lambda and temperature. If temperature goes down, this means your lambda max goes up. So now this wavelength has now shifted out here, and this is where your new peak is, right? So it's a peak which has shifted to the left, but it's now lower than what it previously was. So that's how this graph looks like. Also, technically speaking, all right, we can let this slide. Part B, a galaxy in the constellation of this constellation is moving away. Visible emission spectrum is shown right here. And you are told the lines are at these wavelengths. Compositions of sun and star are similar. What does this mean? This basically means that they emit the same wavelengths. But if this galaxy is moving away, all that light would be red shifted, right? So I took a screenshot of exactly what this was, and I placed it at a slightly greater distance because the wavelength would now be greater. This galaxy is moving away at the speed 21,400. Use information from B1 to calculate in nanometers the observed wavelength of the lowest visible energy emission. Now, because this is talking about the lowest visible energy, this means that energy is the least, so frequency is the least, so lambda is the greatest. So the greatest lambda here was this one. So that's how I know I have to work with 656. So to find this, I use this idea that since I know V, I can use this relationship, delta lambda over lambda equals V over C. So corresponding to this lambda value, I find the delta lambda. Because this is an increase in the observed wavelength, I know this would be added on to what the value was. So it turns out to be 703 nanometers. This wavelength is used to calculate a value for the surface temperature of the star. The calculation does not give an accurate value. State and explain whether this value of the temperature is too high or too low. So you just saw that we did not actually use here. For this, you use the max intensity radiation, right? But instead of using the max intensity radiation, the wavelength corresponding to the max intensity, I just use the maximum wavelength. This is wrong. Because this equation says lambda max T is a constant, and I've talked about this a lot of times in the theory video, that lambda max is not just the greatest wavelength, the one which you have the furthest out to the right, rather it's the wavelength which corresponds to the max intensity, right? So I've taken a wavelength which is greater than what it actually is supposed to be, so my temperature is lower than what it's actually supposed to be. So this is what I wrote as an answer in the last part of this question. So this was not a really easy question. March 24, I guess, I hardly call any papers really tricky or difficult, but March 24 was difficult. All right, so then having done this, Let's go on to magnetic fields and alternating currents. Now, with magnetic fields, there are a lot of questions, many different types of questions that are we can be expected to talk about. Now, for this, again, because I didn't have enough time to prep for this beforehand, let me open this up right now. Let's see from the latest papers what we have is a good question. Again, March 24 also had a good question. I'll show you guys that towards the end. Um, um, yeah, this was a really good question. March 23, paper 42. Again, this is also on the platform. I want to see if we have something good from 2022. So a lot of these questions we've done already. If you guys have any suggestions for some questions, you guys can also let me know and do those as well. Yeah, I mean, honestly, for A2, I can't even find like questions that are really, good because you've done so many of these. Like in the live sessions, we've done 2022, 2023. Before that, 2021, up to 2021, all the questions you possibly have, you already have solutions to that recorded on the platform. October, November 1842, question 8. Right. Let's see. Let's first see what this one is. Let's just do this one first. Wait, summer 23, 6 parts. See, I think we just, yeah, see, we're just about to do summer 23. Okay, we are doing what? March 23. First, let's have a look at that. March 23 is this one. So this one also we've done, but I feel like this is a good question regarding Hall probes. Just want you guys to look at this once and just remember what we did. Especially this part. Yes. So first one, a Hall probe is placed in a magnetic field. Hall voltage is 0. Hall probe is rotated to a new position in the magnetic field. The Hall voltage is now maximum. You know that you have to do this in P5s as well. That you rotate the Hall probe until the field is until you get a max reading. So you know why this is basically because of the sine theta associated with the magnetic field. So the idea is that the voltage is 0 when the plane of this probe, and this is parallel to the field, and it's max when perpendicular. Right, so this is pretty easy stuff that we do know. This thing, remember, we've done state the meaning of n. This is the same n that you have in I equals a and bq. So this is the number density. Explain why a Hall probe is made from silicon rather than copper. So silicon has a lower number density. Lower number density leads to a larger and more measurable Hall voltage value. This thing, let's have a look at this. Remember that always also when you talk about P5s, you can say that you must calibrate your Hall probe according to whatever you have. So this Hall probe gives a max reading of 24 millivolts when placed in a uniform magnetic field of flux density this much. So 32 millitesla is what this Hall voltage reading corresponds to. So it says the same Hall probe is then placed in a field of its direction, varying flux density. Hall probe is placed so that the angle between the Hall probe and the field is the same as the Hall voltage was, 24 millivolts. All right, variation of Hall probe reading is given. So if this goes up to a max of 32 millivolts, I can use the unitary method to find out the new magnetic flux density. This is the most important idea that you have to detect here. If 24 millivolts here, as was given in the question, if this corresponds to 32 millitesla, what does this new max reading correspond to? Right? So this is 32, this is 34, this is 36. So what is the B, the magnetic flux density associated with this? So we just cross multiply. So B would be 36 times 32 over 24. So I think this turns out to be 48 millitesla if I'm not wrong, because I remember doing this question so well. So B here is 48 millitesla. Then everything else is not very difficult here on out, which is that for the max EMF, we use this idea that this is delta N phi over delta T, right? So max EMF, all right. So for the max EMF, you need to identify that this part is steeper. So this has a faster rate of change. So this would lead to a greater EMF, right? So here it goes from this 48 millitesla to 0 in what time? So this is 7.2. This is 8.6. So this happens in a time of 1.4 seconds. And this is 48 millitesla. This is basically what I just wrote down, because N phi equals NBA. So I've just written down this delta B over delta T. N is given as 780, area is 3.6 centimeters. So pi d squared by 4, pi into 3.6 into 10 to the negative 2 squared over 4. So this gives you some voltage value here, which turns out to be 0.027. This, in my opinion, was a really, really good question. Honestly, I don't know when the rest will be uploaded. I'll try to get it done by tonight. But yeah, if it doesn't, Rania, then just check out my YouTube channel. I think I will be able to do it by then on there. I don't know if it would be uploaded on the platform by then. Right, so just watch out for it there. Okay. Similarly, Winter 22, paper 42, question 7 was also a good one. Again, this question, I'm also pretty sure you guys have the solution to beforehand. So this is the insulated rectangular coil of wire, 40 turns, suspended in a cradle from Newton meter as shown. Vertical sides of the coil have a length of 5 centimeters, and this has a length of 3 centimeters. And the initial reading is 0.563 Newton. So that must be the weight of this object, of this coil, right? A U-shaped magnet rests on a top balance that is set to a reading of 0.00 grams. The lower edge of the coil is lowered into the region below the poles of the U-shaped magnet as shown in the side view in 7.2. All right, so then this is shown here. And initially the top band balance reading is, so this is in air, right? It's not touching. Next, we have to see that a current of 3.94 ampere is now passed through the coil. This causes the reading on the top band balance to change to 2.16 grams, right? Explain why the current causes a vertical force to act on the coil. So this is the first thing that we need to see. So these are some poles of the magnet here, which are placed. So if you look here, there's going to be a current in the coil, obviously. So the current is going to be going like this, or maybe downwards in some direction. but explain why the current causes a vertical force to act on the coil. So this is really easy to explain in terms of Fleming's left-hand rule, right? So my second current, my second finger is going to point either up or down, and my field is in a certain way. So because this current is in a magnetic field, so it is going to cause a vertical force on the coil, right? So here, in fact, if I think about this, yeah, so here you just have to explain it in this way, that you say that the current in the coil is in the region of a field of a magnetic field which causes a force which is mutually perpendicular to both the coil, sorry, to both the field and current, right? Determine to 3SF the flux density B of the uniform magnetic field. Now, this is what we are supposed to find. So if I think about this, I have F equals to BIL, and because this is a coil, so it's basically going to be N BIL, and this is really going to be equal to mg, right? Because this increased force, this force which is now exerted on this is also equal to the force which will be exerted upwards on the coil, basically as a consequence of Newton's third law, right? So this coil basically pushes down the magnets, which causes the reading to go up. That should equal the force which is exerted upwards by the magnets on the coil. So here, if I think about it, BIL. So, okay. So again, here you also need to be very careful about what is the direction of the force which is going to act here. Is it going to act on this one, or is it going to act on this side of the conductor? And the answer to this question is that it is going to act on this side. And the reason is this, that because this here, this carries current which is exactly in the same plane as the magnetic field, there would be no force which is exerted on it. Which is exactly why I first labeled this and I went into some thought as to what exactly is happening here. This is upwards. This is right to left, right? So if this is upwards, this, if you think about it, these field lines are not really interacting with this current carrying conductor here, right? But if you're talking about this side in which the current is going in, on this, there is going to be a force. All right. So if your current is parallel to the field, as is the case here, it's not going to experience a force. This is the one which is going to experience a force. So it's 3 centimeters. BI was given as 3.94. This is 3 centimeters, so 0.03. And N was given above 40 turns. E equals mg. So 2.16 is grams as well, divided by 1000 times 9.81. This turns out to be B. Determine what is now the reading on the Newton meter. Explain your reasoning. So again, it's that same idea that because of Newton's third law, this is going to be upwards. So the radium on the Newton meter is going to reduce by this amount, right? So it's basically because of Newton's third law. So whatever this force turns out to be, this is going to reduce by this amount. So explain your reasoning. The answer would be that force downwards on magnet equals to force upwards on coil. Right, so whatever force this is, it would be subtracted from the Newton meter reading. So 0.563 minus whatever that answer is. All right, so that's this then. So that's a section on magnetic fields, alternating currents as well. I would like to show you guys this question here on AC. This was like a pretty typical question, but still nice. AC. All right, so no, I may be confusing the two. There was no question on AC here, but the magnetic field question in this case was also really nice. And if you look at my YouTube channel, so I've also put down a link to a question which was very similar to this. So do have a look at this as well. This question was also nice, especially the last part of this question. Right, so then ideas on quantum, nuclear, and medical physics. So quantum physics, you must be able to like talk about that basically generally in terms of the photoelectric effect. So this is obviously really important stuff, which is proofs of the particulate nature of EM radiation. This is also the question which is asked in exactly the same way, that what are some proofs of the particulate nature of EM radiation? So this is really important stuff here. And then you have all of that stuff following Einstein's equation, all of that part, the graphs. So you have E equals to 5 plus EK max, right? That's how your syllabus writes it. And then all of this stuff regarding quantum physics. I'll also be showing you some different graph questions related to quantum physics. What I feel like would definitely come this time around is stuff on electron energy levels and how it leads to that emission in the spectrum, because that is also some really important stuff. So electron levels, I feel, is going to be on the paper this time out. And instead of alongside electron levels, also electron diffraction as a phenomenon, how that takes place is also something which I feel is going to be assessed. Because again, this has also not been assessed in quite some time. So electron diffraction, you must also be able to analyze the impact of the accelerating voltage on the rings which are formed, right? So this is some stuff which I feel is pretty important regarding quantum physics. Otherwise, you have the normal everyday sort of questions. For nuclear physics, again, I didn't really see quite any sort of a trend with questions related to nuclear physics. It's pretty much the same type of questions. Sometimes you know that you have those really difficult questions which involve mole calculations, and I'll try to do one right now with you guys. And other than that, medical physics also, every time you have like pretty different questions. This time out, the March 24 paper did have a good question related to this on ultrasound and the intensity reflection coefficient calculations as well. So that we'll do in a while. Again, let me just pick out some questions for us to do together. and then we'll go ahead and attempt those. Yes, Usman, but you must also be able to explain this in terms of changes to the momentum, the accelerating potential, all of that. The rings do get closer together, yes, but you must be able to explain that properly. So I'm trying to find out a difficult, like that 4 or 5 marks sort of a question for nuclear physics. If you guys get it, do let me know. I can do anything that you guys want to suggest. All right, I've got it now. This is first off, this is summer 22, paper 41 from nuclear. I guess nuclear is also as a student, I felt that this is the topic in which, I mean, the concepts are not all that difficult, but questions sometimes can be a real pain to do. So I've taken out some of the more difficult ones. Summer 18, paper 42, question 12. All right, Usman, what topic is this? All right, sure, we can do it. I guess nuclear is the most difficult in terms of questions. So this is this question. All right, so A part one, state what is meant by nuclear binding energy. I think this is pretty easy stuff that all of you guys now know how to answer. This is the energy required to split apart all the nucleons, and you need to say that this is in separating them to infinity. If you don't say this, you will lose the mark. So do say this. Sketch a line to show the variation with nucleon number A of the binding energy per nucleon of the nucleus. Again, if you look at this diagram from the book, it's a very detailed diagram, but you can only just make this really simple in this way. Just a sec. Yes. You can make this really simple if you just draw it like this. And if you show that this peak is around here at 56, which is for iron, right? So this is what you have. Sometimes it does ask for you to mark this peak, sometimes it doesn't. So just be safe. In one process, deuterium undergoes this reaction. Obviously, this is fusion. Explain with reference to your line in A2 why this reaction results in the release of energy. So both of these hydrogen nuclei are somewhere along here. So they combine together to form an even heavier nucleus in helium, right? So you will say that both particles have low proton numbers. So they fuse to form nuclear, they fuse to form helium, which has a higher binding energy. Per nucleon, right? Because this is the measure of stability. So it has a higher binding energy per nucleon, so it's more stable. Next part, this is what I want to talk about, is that table 8.1 shows the masses of the particles involved in the reaction in B. Calculate the energy released when 1 mole of deuterium undergoes this reaction. So what we have is that for these particles, the neutron, the hydrogen isotope, and the helium which is formed, you need to find the energy release when 1 mole of deuterium undergoes the reaction. So first of all, what I can do is I can just find out the mass defect, and using that, I can find out, I can then use E equals mc squared to find out that energy, right? So 1 mole of deuterium. So first let's do this. Again, this is just the difference between the reactants and the products, their masses. So you have helium and helium and the neutron. This is this 3.1016029 plus the 1.008665 minus this 2 times 2.01402. Right, again, a lot of people ask me, what do we do? Reaction minus product or product minus reactants? And the answer to this is it doesn't really make a difference as long as you know that this should be a mass defect. So the way I've done this is turning out to be negative, but I'm just ignoring this and going on. And this is U. So when I find E, which is delta M C squared, so 0.00351, U is 1.66 into 10 to the negative 27 kg times 3.0 into 10 to the 8 squared. Right, so this is the energy which would be released in the case of this reaction. So this turns out to be 5.24 into 10 to the negative 13 joules. And now that I found the energy, how do I talk about when 1 mole of deuterium undergoes this reaction? How do I think about this? So if I have 1 mole of deuterium, obviously you can see here from this equation, it's obvious that 0.5 moles is here, 0.5 moles is here. So 0.5 moles of helium is also formed, right? So this is what I've just done. This is basically per mole, right? So for this one, how do I find the energy release when 1 mole of deuterium undergoes the reaction, right? So how do I do this now is that I know this is 0.5 moles. 0.5 moles will correspond to this many total number of particles, right? This is for one such particle, right? So this is my product. This is my product of helium which forms, right? This is how it comes about. 0.5 mole of helium is formed. This is the total number of particles which correspond to 0.5 moles. And I multiply this by the energy which I get from one such particle. Okay. So this value turns out to be 1.58 into 10 to the 11 joules as such. So this is one of those, difficult questions where you also have mole calculations and Avogadro constant calculations. This is how you're supposed to do those ones. All right, what else do we have? So nuclear is done. Quantum physics and medical physics, I'll just show you that they're from the March 24 paper. This is nuclear, a difficult question. Let's see. This was what? Number 22, paper 41. Let me find the question on the electron diffraction pattern. Yes, this is it. March 22, paper 42. And this is question 8. Again, I'm just going to go through this very quickly. State the formula for the de Broglie wavelength of a moving particle. So we know this is lambda equals h over p. So whatever else you use, you have to define this. So you need to say h is the Planck constant and p is the momentum. Electrons accelerate through a potential difference, pass through a thin crystal, and are then incident on a fluorescent screen. Pattern in 8.1 is observed on the fluorescent screen. State the name of the phenomenon shown by the electron at the crystal. We know this is electron diffraction. State what this phenomenon shows about the nature of electrons. So this shows that they have a wave nature. Suggest why the thin crystal causes the phenomenon in B1. So why does it cause diffraction? So the idea is that the de Broglie wavelength associated. No, actually, it's related to this one. Why does diffraction even occur? So we say that the spacing between the lattice structure in the crystal causes electrons to diffract. And so this is like pretty basic stuff that you know from your theory questions as well. The next one is what I want to talk a bit more about. So the electron is accelerated through a different potential difference, new pattern is formed. And if you compare, the rings are obviously much closer here. And you know that these rings are basically showing a fringe pattern. So the wavelength here has basically the fringe spacing here, x has decreased, right? So if x has decreased, so I use this according to this equation that lambda equals ax over d. So if x has decreased, so lambda must have also decreased. And how lambda must have decreased here, if I think about this, is lambda could have decreased if momentum is increased. And how could momentum have increased? Is because of speed has increased because of the accelerating potential increase, right? Because the accelerating potential equals half mv squared. So if the accelerating potential goes up, the speed also goes up. So you write this idea exactly like this is. So you will say that the fringe spacing is reduced, meaning the wavelength is reduced. The de Broglie wavelength is reduced. So the de Broglie wavelength could have reduced if the momentum went up. That could have went up if the speed went up. And that could have only been possible if the accelerating potential difference increases. All right. So that's the answer to this question. Do you guys have any that you would like me to do? Otherwise, we can go forward. Summer 18, paper 42, question 1, 2. Yes, I almost forgot about this. I'll just take this one. Summer 18. Summer 18, paper 42, question 12. Okay, let's see. Question 12. All right, nice question. All right, so this is the question of your choice. Guys, let's go ahead and try this out. Okay, let's go. So state what is meant by radioactive decay. So I think this won't be a problem. Right? So the emission of emissions because of basically changes in the nucleus. You write this in one way or another, you get the mark here, right? So yeah, that's what you say. An unstable nuclide has decay constant lambda p and decays to form a nuclide D. The nuclide D is unstable and decays with constant lambda D to form a stable nuclide S. The decay chain is illustrated in 12.1. Symbols P, D, and S are not the nuclide symbols. Initially, a radioactive sample contains only nuclide P. The variation with time of the number of nuclei of each of the three nucleides in the sample is shown in 12.2. So I have to look at what each of these are, right? It's pretty easy. Because P is just going to decrease throughout, because it's always decaying. It's just going to decrease, right? So this is P. But because D, its first form, then it also decays, this is T. And then because S is not going to decay, it's just going to form. So this is the one which is consistently increasing throughout, this is S. Right? Half-life of the nucleide is this, calculate decay constant lambda P. This is also very easy, honestly. So lambda T half is ln2. So you just rearrange. This is 60 minutes. This is asked in seconds. So you just take this in seconds as well. So ln2 and 60 times 60. This would be your lambda. In the decay chain shown in 12.1, lambda P is approximately equal to 5 lambda naught. All right, now this seems like a technical part. In the decay chain shown in 12.1, lambda P is approximately equal to 5 lambda D. All right. So here I can say that if lambda P is 5 lambda D, so because of the inverse proportion, I can say that actually half-life of P is 1/5 of the half-life of D, right? That's what I can say. Decay chain of a different nucleide is illustrated in 12.3. All right. Decay chain is given decay constant lambda F of the nuclide is very much larger than the decay constant lambda E of nuclide E. All right. So if again the decay constant is much larger, so this means that the half-life of F is much smaller than the half-life of E. Right, again, see how I'm doing this is exactly how you're supposed to do it. I'm not even waiting for the question to come and then for me to think. I'm thinking along as I'm doing the reading. By reference to the half-life of nuclei F, explain why the number of nuclei in F is always small. Right, so this is very easy. So if the half-life of F is very small, so if the half-life is very small, this means they're decaying very rapidly. Does it make sense, Usman? Your question? Oh. All right, guys. All right, good job, guys. Now I was also supposed to do the guest paper beforehand, but somehow time ran out. So I am just going to do this. In fact, let's do this, guys. The guest paper is going to take some time for me to also make. So check out my Insta. I will upload it on there. I will also try to upload this on my YouTube because I have been teaching for more than 6 hours consecutive now. No, I guess maybe like, yeah, almost 6 hours now. So I just need a break, but I will definitely get back to you guys. All right. So maybe I'll also, if somebody is here who's joined from Kohli, I'll also upload the link as in the comments to my section, and then you can check it out. And the Instagram is this. And I'll definitely do this today. It's just that it takes time, making the predicted paper as well. So yeah. So all right, guys, best of luck. Oh my God, the camera is off. I just saw that the camera is off. So all right, best of luck for your paper. Do not stress out. And also at this point in time, I would highly recommend against doing a compilation of the most difficult questions ever or some stupid stuff like that, because at this point, if you do that, it's just going to stress you out. If you really feel like doing something, which you should not, by the way, it's already 7, you should just relax. Is if you really want to do something, you can check out the March 24 paper once again, or if you can check out your older tests and see what mistakes you made. Otherwise, I would just suggest like just reading a few examiner reports, and otherwise just taking it easy and just going into the exam with a fresh mind and on a good night's sleep. All right. No looking at the thresholds and stuff like that. Also, that's just going to unnerve you. Whatever is going to happen is going to happen. So yeah, just do your best and come out of the exam hall with this satisfaction. And you did justice to the syllabus content. All right. So best of luck, guys. We're all praying and rooting for you. So hope you get more than what you deserve. Hope that you get the best of grades. Bye bye.